lunch with Chris and slide us up. Okay, great. So our next speaker is Chris Heunen, and he'll be speaking about semantic foundations for probabilistic programming.
Thank you. My name is Chris. Thank you for having me. I come from the University of Edinburgh, but I'll be reporting on joint work with a lot of people from the University of Oxford. And actually, Sam Statham was supposed to give this talk, but he fell ill and couldn't make it, unfortunately. So with 2 days' notice, I'm here. I'll tell you all about it. And Hongsyuk is already giving the next talk, so he also couldn't really talk about this. The other thing I should say is I'll be here for the rest of the month, and I'm very happy to work on anything you can think of related to this or anything else I'm interested in. So we two gonna have a chat. And I'll be talking about semantic foundations for probabilistic programming. I'm going to start out to set the scene by insulting all of the audience. So there's sort of 2 halves to this, semantic foundations and probabilistic programming. I'll have 2 slides on each. I hope you're not insulted that it's a bit basic, just to make sure we're all on the same page. Okay, so first, semantic foundations. That's about if you write a program, you don't just want to write the program, you want to prove that it does what you claim that it does, right? And to be able to do that, you need some sort of mathematical model to do your proof in. So the idea of semantics is you have your big bag of programs. Here's 2 of them. We're going to assign to each program a semantics. So some sort of mathematical object in some universe of mathematical objects. And we're not just going to do it willy-nilly, of course. We're going to do it in such a way that if 2 programs are related to each other in some way, for example, they're concatenations of 2 statements, then the thing I assign to this combined object over here has to have a similar kind of relationship to the two constituents objects I assign to those 2 statements. So the idea is that these mathematical structures here are going to reflect the structure of the programs. There's various ways of doing this. You could do this operationally. You could think as these kinds of mathematical objects, I might take literally some sort of state machine that sort of executes the trace of this program and keep all the implementation details along. And that's very handy if you want to think about efficiency of a program. The other thing you can do, and that's what I'll focus on today mostly, is denotational semantics. So there you don't really care about the actual implementation details of a program, but conceptually sort of what it does. And the point, and that's most useful if you want to talk about correctness of a program. So what does it say to be that a program is correct? You first sort of need to know what it means, what it's correct against. And the motivations for doing this are typically, and especially in this probabilistic programming community, to ground the programmer's intuition in a sense. So most people that work with probabilistic system have some sort of semantics in mind, and there might be some sort of intuition that all the people in the community agree on, but sometimes it's not clear, sometimes it's not outspoken. And especially if some fancier features come in, like higher order functions, for example, it's not clear what the corner cases are. So it helps to make this explicit. The other thing you can do is, so we might not know a lot about these programs, but we might understand these mathematical structures very well. So for example, if these 2 programs get set to the same semantics, have the same meaning, you could say sort of they're both implementations of the same algorithm. And conversely, you might think that 2 programs compute the same thing, but if they have different semantics, that's ostensibly false. Right? So you can check whether your carefully designed program transformation is actually careful. Typically, these mathematical objects, traditionally they're taken to be certain kinds of partial orders, domains, where the partial order says sort of this partial evaluation of the program is larger than that one. But in principle, it can be any structure whatsoever. They can be objects in any category, and we're going to use this later on. Okay, then about probabilistic programming. Dan's talk set this up very nicely. I'm going to continue in that kind of spirit. As far as I'm concerned, it all starts with Bayes' law. Here's Bayes' law. The probability of A given B is the same as probability of B given A times the probability of A, all divided by probability of B. It's just a fact of life. So in other words, if I take out this normalizing constant P of B, that says that probability of A given B is proportional to the probability of B given A times that probability of A. Or in words, the posterior is proportional to the likelihood of an event happening times the prior. And this is going to be a slogan I'm going to use for a while. And the kind of programming language that I'm going to talk about, it's called Anglican. It's a fork of church, hence the name. So basically what they've done is they take functional programming, sort of something like Haskell, the purest functional programming language you can think about, and they add specific constructs to talk about probabilistic models and systems and inference algorithms that correspond to these elements of Bayes' law. So for example, if I give you a prior, in the programming language, you can sample from that prior. You can ask, please give me a sample now from this distribution you gave me. The likelihood corresponds to a primitive it's called observe. So suppose you're writing some program, you've sampled your prior for a while, and then you get told, look, in the real world, this data happened. You observe that event, and that influences. You can draw inferences from that. And then there's something called normalize. So I divide it by this constant here that's sort of hidden in this proportional to symbol. It's going to be explicit in the language. So we want to end up with a probability distribution at the end of the day. So sort of the weight of the whole space has to be 1. I'll explain it later in more detail. Okay, so here's the overview of what I'm going to do. So I'm going to develop semantics, denotational semantics for this kind of idealized Anglican probabilistic programming language. I'm going to interpret types as measurable spaces. It's a type language, so the meaning of a type is a measurable space. And I'm going to interpret programs, statements. I'm going to take a very academic point of view and call them terms. I'm going to interpret terms as kernels, so terms with an input type and an output type, if you like. And specifically, that means that the closed terms, the ones without an input type, the ones that just compute something, are going to be interpreted as measures on the type, on the measurable space that corresponds to its type. And then inference normalizes these measures. This is more or less standard since Dexter-Cozen, or maybe even earlier. We're going to add some features to this basic first order setup. Specifically, I'm going to talk about higher order functions. So that's a program that can take a function as its input and pass it on as an output and sort of change the argument in the meantime. And that is going to open up a can of worms, and we'll see how many details I can tell you about that. So specifically, I said we're going to interpret types as measurable spaces. For example, the type of reals. So this is something in the programming language. I'm going to interpret as the actual real number space with the Borel sigma algebra. But if I also want higher order functions, right, I need to have some measurable space to interpret the type of functions from reals to reals. And it so happens that there's rigid results saying there cannot be any sigma algebra whatsoever, no structure of a measurable space whatsoever, on the set of functions from R to R. So something needs to give there. We're going to find a solution for that. And that's going to have some other issues that I'll talk about. I should mention this is based on a LIX paper this year. Especially, so this is mostly Sam's work, and these two things are new as well. It's not yet published anywhere.
Sorry, what do you mean by there is no measurable structure on that space of function? You can always put the sigma.
Yes, so I left out some crucial assumptions there, so it's in this paper if you want to look it up. And the crucial assumption is that you want evaluation to be a measurable function. Suppose you look at the function space of functions R to R. I have the space R. You can take the product of them, and then a function that evaluates a function on a point to R. Let me write it down. So this function. It stands to reason that we want that function to be measurable. The result is there is no measurable structure or measurable space on this set that makes this function measurable.
So again, sorry to be a pain in the neck, but you can always take the sigma algebra generated by this map, right? So there's another thing when they're telling us You want Brilliant subsets of R to be measurable?
Yes, the thing I'm hiding here is we want this product to be the actual product of measurable spaces. It's not, so it's a measurable structure of a measurable space I'm putting on here. And then this thing is fixed. It's not a structure of a measurable space I can put on the totality of this. That you can do.
Okay. I see.
So there's obstructions here, is the point.
They're interesting ones, or they're, I mean, is there some...
I don't know of a good application for them, but in principle that could be.
If you move to equivalence classes with respect to a fixed measure, then you're okay again.
Okay. I was about to ask you, and with ideals of negligibles, you can also do that? Or do you have to commit to a full-blown measure?
I mean, it can be the class of all measures absolutely continuous or equivalent. That's of course, but that's kind of almost a tautology. My first statement. But actually, I don't know what ideals are.
Thank you.
Oh, thank you. Okay, so here's a running example to try and get you to understand the kind of programs in this language that I'll talk about. Suppose we toss a fair coin, we get an outcome x. Then depending on that outcome x, I'm going to set up a distribution with one of exponential decay with one or two rates, either the yellow one or the blue one. Right, if it comes up heads, say we do the blue one. If it's tails, we do the yellow one. And then someone tells us that decay is so and so much. What does this tell us about our original coin flip? Right, so this is sort of an informal description of the experiment. Here's how you would write it down in Anglican. So the 4 lines of the experiment pretty much correlate one-to-one with the 4 lines of this program. I just said, throw a fair coin, call the outcome x. This is a Bernoulli distribution, you sample from it. Depending on this rate, if it comes up heads, then the rate's going to be 2. If it comes up tails, then the rate's going to be 1. Right, so you get the yellow and the blue one, and then we set up the distribution we're interested in, and we observe that something happened. And then we return x. So that sort of calculates for us. This compiles to a program that gives you the probability, the posterior really, on x. So what does this program mean? What does it do? Well, naively, you could try and just run through all the possibilities, like an execution tree. So here's the first line. We sample from the Bernoulli distribution. So it either comes up head or it comes up tails. So probability half, it comes up heads. Let me call it true. Probability half, it comes up false. Right. Then if we're in this branch of the tree, if x was true, then here I'm going to assign 2 to r. Let me get back to score in a minute. I'm going to return true in the end. If it comes up false, I'm going to assign rate 1. I'm going to return false. But in a sense, so this trace has twice as much weight as this one. And that's what the score is supposed to say. We're going to sort of keep that score. We're going to accumulate the score when we do the execution. Okay, so here's my slogan. Posterior is proportional to likelihood times prior. Here we have our likelihood and our priors. So this is the posterior, the measure at the end. Except that it's not really a probability measure. So if I wish to take this at face value, the probability that x was true is going to be 1. Probability is false is going to be a half. That doesn't add up to 1, so it's not a probability measure. I need to normalize it. Total weight of these scores is 3. So I need to divide by sort of 3 times a half. So at the end of the day, the posterior is going to be 2/3 chances of true, 1/3 chances of false. And the model evidence that I've divided by, I'm going to remember, was 1.5. Is the example clear?
I think I missed the score. Where is the score coming from?
This one. It comes from that observe, if you like. So observe is the key word in the language. Sorry. I think I'm using them interchangeably. Sometimes it's score, sometimes it's observe. I tried to color code them. So red, it means red.
So how can observe return to?
So one way to understand this is just imagine each execution has some one global variable that keep track of the current score of the particular execution. So whenever you get execution encounters or observe, it evaluates some expression there. Essentially, you look at probability density functions, evaluated with respect to the given data, and then that data will become a new score that gets multiplied by your current score. So this global variable tractor score that keep getting multiplied by various observed statements. That can compute the likelihood score.
Sense?
Shouldn't the likelihood be a probability as well?
Not necessarily. But after you normalize, of course it will be.
The density.
Right.
Oh, okay. So that's
So here there were only two possible execution traces because it only depends on whether the coin comes up heads or tails. In other words, because this was the Bernoulli distribution we sampled, but it could be many other possibly continuous distributions. If it were a normal distribution, for example, there would be not only infinitely many execution paths we could take, there would be uncountably many. And that would be a problem. We couldn't sort of add uncountably many non-zero numbers. That's why I'm going to use measurable spaces. I'm not really sure how up to speed everyone is with this. But the basic point of it is that the probability of sampling one specific point is always going to be 0. And yet, if I ask that my sample lies within an interval, it's going to be a non-zero probability. Right? So all of these slices, these uncountably many slices, are all 0, but they add up to something non-zero. And that's what measure theory sort of solves for you. So literally a measurable space is a set with some family of subsets that we'll call measurable. So these are the events you can observe, sort of. And a measure on that space is a function that assigns to a measurable set a number in such a way that it takes disjoint unions to sums, but countable ones. Countable is the key word here. That's just to make sure we're all on the same page. So here's the official language I'll be talking about. It's a typed language, so it has types. The types I'm going to allow are, first of all, the real numbers. If I have any type A, I'm going to allow a distribution type that takes probability distributions on A. And I'm going to allow finite products and countable sums. So specifically, once I have this, I can build, for example, Booleans by doing 1 + 1, or I can take naturals by doing a countable sum of 1. Okay, that's the types. And terms come in two types, come in two variations. There's going to be program statements that are deterministic, that don't depend on any probability distribution or sampling. And later on, there's going to be one that are probabilistic. So deterministic terms are sort of the boring ones. You can have variables, you can have things to make these sums and products work nicely. The interesting one is any measurable function whatsoever, I'm going to allow as a statement in my language. So specifically, something like the Bernoulli distribution that we've just used, you could see that as a measurable function from the singleton set to the set of probability distributions on R. So those are allowed terms in my language. So here's a bunch of examples. So this is supposed to say, given no context, the following is a deterministic term, 42 of type real, right? Because 42, if you like, is a measurable function from the singleton set to the real numbers. And you build all these kind of things. Okay, and then there's the probabilistic terms. These are more interesting. I'm going to allow sequencing just so I can do functional things, return and let. And here's the two primitives that we're going to add, these score and sample, observe and sample. So score just says the thing I've observed. If t is some real number, deterministically, not depending on probabilistically on the context, on the input, then score of t is going to be, yes, that's the one. It's going to be a singleton, a term of type 1, but it's going to be a probabilistic term. And similarly, if t is some distribution on A, then sample of t is going to give me sort of an element of A. It's a term of type t, of type A. Okay, so these are two of my colors. Here's the third. I'll call it normalization. I'll have a whole slide on it in a minute. Okay, that's the language. Now I'm going to give the semantics. I'm going to build this up hand by hand. I'm going to sort of add features to both as we go along. So as I said, we're going to interpret types as measurable spaces. Deterministic terms are going to be measurable functions. So a deterministic term t in context gamma of type A. It's going to be a measurable function from sort of the meaning of gamma to the meaning of A. Probabilistic terms are going to be kernels. So these are functions of this type from a probabilistic term in context gamma of type A is a function from the meaning of gamma times the sigma algebra of the meaning of A. So these are the measurable sets in A, two numbers, in such a way that if I fix the first argument, if I take an element here and fix it, the function I have left is going to be a measure. And if I take a measurable set and fix that, the function I have left is going to be a measurable function. Okay, so here was my language. It's sort of obvious how to interpret all of these things and how to interpret that. Let me talk about these two, because they're the interesting ones. So if I have a term score of t, right, it has this type. It's a probabilistic term, so it's going to be a kernel from gamma times sigma algebra of 1, just a discrete measurable space on the singleton element, to a number. So here's my discrete element. Basically, I need to give it a gamma, and I need to produce a number, and I'm just going to evaluate t sort of on that input. And sample sort of does it in the other argument, if you like. So if you track through the types, now you need to evaluate t not just on gamma, but also on some measurable subset. And then the let basically comes down to integration. If you want to chain statements together, it comes down to integrating out the middle variable, the middle type.
Sorry, just I've lost track. So small gamma is an instance of a environment, capital gamma or something? Or?
Yeah, small gamma is an element of this measurable space, sort of bracket, gamma bracket. See, I was hesitating whether I should put these explicit formulas because they put people to sleep typically, while you're awake. Okay, so here's the running example. We saw that this is a well-typed program. It makes sense. Now, what does it mean? We can sort of interpret it and find its semantics. Well, so the meaning of a program, it's a closed program, has no input, so it's going to be a measure on the space on its type. So in this case, the type, it returns x, so its type is either true or false, it's a Booleans, with the discrete sigma algebra on it. And the meaning of this is a measure on the two-element set. So I need to tell you what sizes, what measures we assign to all possible measurable subsets. Here's all 4 of them. And we calculated before what it does. The empty set always has measure 0. These were the two probabilities, well, not probabilities, but measures we calculated. They added up to the whole space having measure 1.5. That's the meaning of this program. Okay, now let me talk about this normalization procedure. So this is I'm going to allow statements of type of the form norm of t, where t is some type of term A. And it's going to have this type. Either it's going to be a real number and a probability distribution on A, or it's going to be one of those two singleton sets. And these are going to represent some errors. So I think of a normalization of t as I remember the model evidence, and I remember the normalized posterior, or some errors. So how do I interpret this? Well, it's a probabilistic term. So it's going to be a kernel in general. So it's going to have this type. I need to find a kernel of this type. And remember, a kernel, the definition of it is if I fix the first argument, if I leave out this, the thing I have left here is going to be a measure. Right, so this thing is a measure. And of course, if I divide by the weight of the whole space, I'm going to get a probability measure. Right, so this is the posterior, then I'm going to put in there. And this normalizing constant is I'm going to remember that. It's the model evidence. It's going to go in there. could, of course, be the case that this model evidence, this normalizing constant here is 0 or infinity, and then I'm in trouble. I can't divide, so I'm just going to put that in the errors here. Okay, so that's what normalize does. So here's our example program. This is the meaning we just assigned to it. Let's normalize this thing. So that means I normalize this distribution. And it's going to look like a fair coin, well, not fair, a coin with probability 2/3. The model evidence was 1.5, and this in 1 just means it's in this term of the sum. It's not one of the errors. So now we can prove all kinds of program transformations correct. So here, for example, is sequential Monte Carlo, which basically one of the key steps, and it comes down to this statement that you can sort of unroll once and discard the sample if it's no good. So this is sort of a more efficient version of that. And you can compute the interpretation for both sides, and they come out to be the same. So this step is actually justified. And of course, that's what programmers have in mind when they do this. And there's lots of more examples you can calculate. You could do importance sampling, where, for example, suppose we know that exponential distribution is hard to compute to sample from, but a normal distribution is easy. And we can try and use the normal one to simulate sampling the exponential one in such a way. And you can prove these two statements equal. The meaning of them is equal. Another one I could do is I could unroll this one further. This sort of first I score by that, and then I score by 1 over this. So it's also equal to that. But if you normalize all of them, so these two programs were the same, so if I normalize both of them, they're still going to be the same. So let's suppose I don't just normalize the whole thing, but I normalize the first two, and then use that to go on, and then normalize the end result. That's not going to be the same thing, because if you normalize these two, effectively you'll be sampling the Lebesgue distribution. So that's going to give sort of the infinity error. So you normalize at the end of a whole run, not halfway, and keep going. And of course, people know this, but it's good to see how it actually works. Let me skip this. There's a lot more examples you can have a look at. Maybe this one is a fun one to look at, because I think Vincent was asking about it yesterday. Suppose we look at this program. First, you sample the beta distribution, and then you observe that some Bernoulli based on it is true. Another thing you could do is first observe and then sample another beta, sort of a beta with different parameters. So this is called conjugate priors. This is the conjugate prior for that. So you can't quite switch these lines, but almost up to changing the distribution. You can prove that these two semantics are equal. Right? So that means using computer algebra, if you like, or just pen and paper, you can prove that they're the same. But in the programming language, in the probabilistic programming language, they are different programs. So that's sort of the two sides of this question yesterday. Let me push on to talk about higher order functions. So these are functions, if you allow your programming language to write functions that take functions as input and pass functions through as output. And these things actually get used. Here's a paper of Dan's, actually, in some horrible Lisp notation. But the point is, this defines some function, an Indian Buffet process. It takes a measure, and it actually uses a measure later on. And of course, measures are function types. Right? So it takes something, a function type, and uses it. So these things get used, is the point. And Anglican actually allows the use of higher order functions. Except they don't really know what it means and if it goes well all the time. Okay, so here were the types we had before. We're going to allow function types now. If A is a type and B is a type, I'm going to allow the type of functions, the space of functions from A to B. But as we saw before in this specific sense, R is a type, so I should be able to make the type R arrow R. And I want to interpret types as measurable spaces. But we know we can't do this. Right? So R arrow R, if I literally take all the measurable functions from R to R, that's no good. We need to take something else to interpret this type. Operationally, that's easy to do, but I'm focusing on the denotation now. So how do we handle this? And This is where category theory comes to the rescue. I know categories get a bad name occasionally, but they're actually useful, as I'm going to show you now. So we were interpreting our types as measurable spaces, and we know that there are not enough function spaces in there to allow us to interpret function types. Right, so what we're going to do is embed this universe into a larger one that does have enough function spaces. Specifically, we're going to use sheaves on measurable spaces. So these are certain types of functors that assign to each measurable space a set. And I want them to preserve countable products for technical reasons I won't get into. The point is, this is a fine universe of mathematical structures that we can interpret our programs in. And it does have all function spaces. So basically, we've sort of completed this universe by throwing in all function spaces formally. And this embedding here, the UNITA embedding, preserves all structure you could dream of. So everything that held here still holds here. Okay, but now we do have function types. Actually, I'm slightly lying. There's a bit more work you have to do. So where did we go? We had this type, right? If A is a type, then I allow terms that have it as type probability distributions on A. So, and I didn't really talk about how we interpret that, but that's basically by this thing called a G-ring monad. So it's something, if you take a measurable space, A, then the probability distributions on A are again a measurable space. So that's a map that goes here. If I want to extend my semantics to over on the right side, I'd better have a similar thing over here. Right, turns out you can do that by abstract nonsense called can extensions. And it works perfectly. There's one thing I'm brushing under the rug here, which is for this trick to work, for this thing to exist, I can't take all measurable spaces. I need to have a set's worth of them and not a proper class. So you need to restrict to nice enough measurable spaces. Standard Borel spaces will do, for example. Okay, so now we have a larger universe where we can interpret all our stuff. So you might ask, what do these function types look like now over here? So for example, this problematic type of R, arrow R, what is it? It's some sort of object here, but what does it look like? And it turns out if you ask about sort of what its points are, what its elements are, if you like. So what sheaf does this thing denote? Turns out to be exactly the random functions. And that's a name people have for measurable functions from a probability space times R to R. Is that clear? Now finally I'm going to do two things to this higher order semantics. First thing I'm going to do is, so we can do this formally, it's all nice and well, but these are fairly complicated mathematical structures. Let's try and find the easier description for them. And you can do that. So here's my new semantics from now on. Instead of these sheaves, I'm going to work with something we'll call quasi-measurable spaces. So I define that to be a set, not now with a family of subsets I'll call measurable, but with a subset of functions from the reals to my set that I'm going to call measurable. And they have to satisfy some axioms. So a measurable space, you have to distinguish measurable subset, they have to satisfy some axioms. Now I'm going to distinguish some functions into my space that satisfy some axioms. And the axioms I wanted to satisfy is I want to be closed under precomposing with measurable functions R to R, measurable real functions. I wanted to contain all the constant functions. And I wanted to have sort of countable branching, if you like. So specifically, if some function f from R to n is measurable, and for each n I have an element of my sort of abstractly measurable functions here, then this function I also want to be abstractly measurable. This might be funny notation to you. I mean this function. You get some real number. You apply f to it to get a natural number, and apply the f-teeth function g to my number. Okay, so those are quasi-measurable spaces. Any measurable space is going to be an example, so that's sort of the intuition behind them. If X were an actual honest-to-goodness measurable space, then I can just take for this set M to be all measurable functions R to X. It will satisfy those axioms. But there will be more quasi-measurable spaces than measurable ones.
Well, what measure are you taking on n?
Discrete one. Measurable, right? No measure, measurable. So just a discrete sigma algebra. There's no measure of big anywhere. If you look at these things and sort of the homomorphisms that preserve the right amount of structure, they will form a Cartesian closed category with countable sums. And that's a fancy name for the kind of category I need to interpret my language in. And so Cartesian closed means I can have my function types. Countable sums means I can have my countable sums. And the funny thing about this is a term, so suppose I have a term of first order type that doesn't involve any sort of higher order nonsense in its input or output type. It might involve some, it might be built up, it might be a concatenation of statements. Halfway you use higher order types, but as long as the input and output types are first order, then its interpretation is going to be an actual measurable function. Right? So it's not going to live in this sort of extended world. If its type lives here, then its interpretation will live there. So it's a conservative extension, if you like. Let's get this too. And the final point I want to talk about is recursion, briefly.
Let's go back to I still don't get the relationship between quasi-measurable space and measurable space. What is...
So any measurable space is an example of a quasi-measurable space, but there exist quasi-measurable spaces that are not of that form.
So we could look at sort of subsets and kind of or overlap between the...
I can draw a Venn diagram if you like, yes. Is that what you mean? So here is measurable spaces. We live inside all quasi-measurable spaces. Is that what you mean?
Oh, okay. Right. Yeah, okay.
So the second
For inclusion?
is not always the case, right? It's not always true that is that saying that the singleton is measurable? If x is measurable? Sorry. First of all, I have a more basic question. What does it mean? I mean, of course, it means what you wrote, right? That Mx satisfies all your axioms. But can you recover the sigma algebra you started from on X?
That's a good question. I don't immediately have an answer to. I suspect so, but I don't know for sure.
Because it's one thing to say that if I give you X and it's sigma, then you can construct your Mx and it satisfies all your free axioms. But it's another one to say that you can recover the initial structure. Right? I mean, a priori, right?
I don't know off the top of my head, but I think so.
So do I read correctly in this case that the second axiom says that singletons are measurable? If
Singleton?
X is measurable and I take for Mx all the measurable functions.
Oh, you mean if X is a singleton set? And you take for this?
No. Every singleton in X. Or maybe I'm completely confused.
I mean, when this definition doesn't assume that there is any measure on X, right? It's just a set.
Yeah, it's just a set,
I
no
think
structure.
Marcel was asking, suppose it was a measurable, had a measure algebra defined on it.
Yeah, exactly. So you say, example, you say, pick something that already has a measurable structure, and I can make that quasi-measurable structure out of it.
Yes.
So, and you're saying, so the recipe is to say that you take for Mx all the measurable functions like this. And so now I apply axiom 2, and that tells me that in particular, constant functions will be in that Mx. Is that correct?
Yes, so to show that this example satisfies the axioms, you have to show that constant functions are measurable, which is true.
No, it's not true. I mean, it's true only if you
So
have...
measurable means the inverse image of a measurable set here is measurable there. So there's only two ones here. So the only inverse images you can get are empty and the full thing, and they're both measurable. Is that what you mean?
Another useful intuition is the view Mx as a set of random variables on X. So this is try to directly formalize random variable instead of sigma algebra.
Yeah, that's a nice point to make. Let me try and explain it to you after, because I want to set up Dane OS to talk about something for 10 minutes.
I'm just saying it's not true that singletons are measurable, not always, right?
But these are not singletons.
They're constant
They're
functions.
maps from R to X, which are constant functions. So when you take any
Yeah, but a
measurable
constant
set-
function from R to X looks a lot to me like a singleton.
No, it's not. It's not at all, right? Because whenever you take any measurable set in X, you take the inverse function. Either this measurable set includes the point, which is the image of the function, or it doesn't, and therefore the inverse image will either be the whole space R, or will be the empty set.
Right.
And these are both measurable, right? And that's
Right.
the definition of measurable.
Yeah, but so you're saying that the indicator function of one of a singleton of small x.
This is not an indicator function. This is a constant function. I think.
Okay, I'm confused. Okay, I'm
think
right.
of measurable functions from X to
Okay, sorry.
Chris, maybe you can stay for 3 more minutes.
Yes, I'm nearly done. This is the last slide.
Right.
So what was I going to say? All right, I haven't talked about recursion so far. So these quasi-measurable spaces so far were a set with some structure on it. To talk about recursion, we need to have some sort of fixed point operator on this set. So instead of just a set, I'm going to ask that they are ordered sets with a fixed point operator. And one way to do that is to ask that they are so-called omega complete partial order, some nice type of domain. Which means this is a partial order that if you have an increasing sequence, non-decreasing officially, then there is some sort of ideal point at the top of it, some least upper bound. Okay, so a quasi-measurable space I'll call ordered when X is not just a set, but actually one of these things. You can compute fixed points. And moreover, this set of random elements, if you like, of X, of functions from R to X that I'll call measurable. I want it to be closed under this operation of taking least upper bounds. So remember, M is so all functions R to X, if X is partially ordered, then this set of functions is partially ordered just pointwise. And if I can take suprema in X, then I can take suprema here pointwise. But that's not necessarily a measurable function again. I want M to be closed under that operation. And a funny thing is that any domain, any omega DCPO whatsoever, for example, the unit interval, will be an example of this. If you take the right sigma alpha on it. And again, this gives the right type of category for me to interpret my language in. It's a Cartesian closed category with countable sums. Okay, so just to sum up, let me skip that. I've told you about foundational semantics for probabilistic programming. Right? We had this idealized Anglican language, and I've developed a species of mathematical structures in which we can interpret faithfully pretty much all the structure you want from these probabilistic programs. We can have continuous distributions, we can have soft constraints. I didn't talk about commutativity. We could have higher order things, and we can have recursion all at the same time. And you can use this to, first of all, verify that program transformations, for example, in the Anglican compiler, are actually correct, that there's no bugs, that it's safe. You might also go the other way and sort of suggest program transformations as optimizations. And what I'd like to think about in the future is something like I talked about yesterday as well. I think if I have a bunch of programs that get better and better, so to speak, when do they approximate some sort of ideal program? So how can you simulate, for example, sampling some normal distribution? And what does that mean? Okay, and I'll stop there. Thank you very much.
Time for questions, I think.
So one thing is there a clear relation between this semantics you just showed us and the pre-chief semantics?
Yes. I skipped over that bit. So by pre-chief semantics, you mean this one?
Yeah.
The quasi-measurable spaces that I told you about are precisely the sort of the largest extensional subcategory of that, the largest well-pointed subcategory of that. That's how we got it.
I see. And the other question is, well, I mean, there's a long-standing issue in domain theory about finding a Cartesian closed category closed under the probabilistic power domain. So it seems you found something which you can use for a similar purpose by a different means. I mean, do you have
Yes, I'm aware of that, and that's something I want to work on. So this is fairly fresh, and it's definitely not fully developed.
Yeah.
So thank you. That's an interesting direction, surely. Yes.
So I have a question. So in my work with Cameron and Nate on computable analysis, mostly we interpret probabilistic programs as not merely measurable functions, but functions continuous on a measurement set. And for any probability measure on a computable Polish space, there is going to exist one of these functions from, say, a unit interval. So could it be that we could, first of all, do you see, does continuity on measure one set show up anywhere here? Do you think you could use that as a basis rather than measurability? Of course, you wouldn't want to have constants in your language which are merely measurable functions, but maybe all the constants are, yeah.
I don't know. It's an interesting question. I don't know. So there are some issues if you want to talk about continuous density functions. We're not really sure how to handle them, how these fit in. But this setting is new to me, so I really can't answer.
Okay.
I have a question about the random functions. What kind of notion of random function do you have in your model?
So I think you're talking about this point here. So correct me if I'm wrong, but I understand that people by random function from x to y mean a measurable function from some omega times x to y, where omega is a probability, comes with a probability measure.
And also generally
some
that
modulo, some conditions on different omegas.
Is that the same thing as a probability on just the space of all functions from x to y?
Sorry, a prelude on?
A probability distribution on all functions from x to y? Or all measurable such functions? Or
But you could carry.
So here what's going on is if you apply extended Giri monads on arc arrow R in this pre-shift category, then you will get intuitively what you should get is a probability space on functions. But that's all defined in terms of this pre-shift abstract nonsense. So, but what we found is that we worked it out. What does it really say? What it says is it's just said. So this is intended to describe what probability space or probability measure on function actually look like. And then it turns out probability measure is actually a measurable function from some probability space times the source measurable space to the target measurable space. So if this x and y are real numbers, it becomes very much like continuous time stochastic process.
but measurable.
Yeah, measurable continuous time stochastic process. And then one additional thing that's going on here is because the Giri monads, if you extend it, there is some big quotient is going on. So there are some form of equivalence class, and they make a bunch of things equal. And that intuitively corresponds to say the particular choice of this underlying probability space doesn't really matter. So if you change underlying probability space from omega to omega prime, but things about random function, but like measure this stochastic continuous time stochastic process on omega and continuous time stochastic process on omega prime are somehow related, then they are considered equal in this domain.
okay.
Any more questions? All right, thank you very much.